Welcome to class number 19 of transport phenomena in mesoscopic and nanoscopic systems. We are now ready to move into the transport and we are ready to gradually go into the current equation from non-equilibrium Green's function formulation. Okay, so this formulation which we are using right now, this is known as the non-equilibrium Green's function formulation. So Green's function we have already discussed before, and non-equilibrium because we are not dealing with an equilibrium system. So it is non-equilibrium Green's function, simply written as NEGF formulation. Okay. Now, first let us kind of recapitulate what we learned a little bit, and let us also discuss about the density matrix. So we discussed the density matrix in the last day, and we defined density matrix rho as just the Fermi function of this matrix H minus mu I, where mu is the equilibrium Fermi energy. So this is the equilibrium Fermi energy. Okay. Now we can readily convert it into a space basis. So this equation we wrote assuming that this Hamiltonian H is written in the eigen energy basis or eigen function basis of this Hamiltonian. But we also argued that since this representation is valid in the eigenspace basis of the Hamiltonian, this should be equally valid in any other representation, and we can readily transform this representation in the eigenspace basis into a normal space basis or real space basis by using appropriate transformation matrix. And I will not go into the detail of how it is done. I think you are kind of mature enough to figure it out. So I'll just write the result that if we basically convert it into a space basis, we basically get the density matrix in space basis as rho r dash, which is basically equal to summation over alpha phi alpha r f0 epsilon alpha minus mu phi alpha star. So this is the complex conjugate of phi alpha r, where alpha is basically the wave function corresponding to the eigenstate alpha. Okay, it is actually r dash here instead of r. Yeah. So we can hence readily write the matrix notation. So here I have written an element with rho r and coulomb r in the space basis. Okay, so if we write it in matrix notation, this would readily be written as rho equals to, so I will label the eigenstates as psi because phi I have denoted to label the eigenstates of the contact. Okay, so I will just write it as psi alpha here and psi alpha star here. Okay, so rho is equal to summation over alpha f0 epsilon alpha minus mu, and then the then the matrix psi alpha dagger. Okay, so this psi alpha is basically a column vector, and psi alpha dagger is a row vector. Okay, so note that this thing psi alpha dagger psi alpha, this is basically a number. This is basically a number and it denotes the inner product of psi alpha with itself. Okay, and this is a number because this is a row vector and this is a column vector. So when you multiply this row vector with this column vector, it basically becomes a number. It's an inner product. Okay, however, this is not a number, this is a matrix because this is a column vector here and this is a row vector. Okay, so this is basically a matrix. So row basically becomes a matrix here. Okay, so this again we can write in another format, in an integral format, which is integral over dE f0 epsilon alpha minus mu, then summation over alpha delta E minus epsilon alpha. So I'll probably run out of space here, but phi alpha. So let me write it from the left. Dagger. Okay. Now this part over here, as you can understand, this part is the local density of states inside the channel. So this is LDOS, local density of states inside the channel at energy E. Okay, this part means including the summation. So this entire part over here, this is basically the local density of states inside the channel at energy E. Now note that we have earlier derived that psi alpha is so this is again a matrix equal to GS, okay, S alpha to be precise, and S alpha is equal to this matrix tau times phi alpha, where phi alpha is basically the eigenstate at energy alpha in the contact. Okay, so this we have learned earlier, that this source term S is equal to tau times the wave function inside the contact phi alpha. Okay, so we replace this psi alpha in this equation by this term over here, and we basically get, so this is this matrix rho. So rho is equal to integral over dE minus mu, and then summation over alpha delta E minus epsilon alpha multiplied by G tau phi alpha. So I will just put this delta in the middle so that it's easier to understand. So summation over alpha G tau phi alpha, all these are matrices, I am not writing the matrix notation here for convenience, and delta E minus epsilon alpha, then phi alpha dagger, tau dagger, and G dagger. Okay, and now I basically enclose this term over here. Now note that this is again a special term which is basically equal to the local density of states of the eigenstate alpha inside the contact. So this is basically LDOS inside the contact, and this is basically given by our spectral function. So we write it as integral of del E f0 E minus mu. This is not a very rigorous way to prove, but the actual method is difficult, and being from engineering background it might seem more difficult. So I am just proving it in a logical sense to show you what equation we basically get. Okay, so G tau, the spectral function of the contact, which we term as R for reservoir here. Okay, reservoir basically means the contact, and tau dagger, G dagger. Actually this summation would come inside the brackets to call it as this spectral function. So we just remove this from here. So this entire thing is the spectral function actually. This entire thing is the spectral function. Okay. So we also remove this thing from here. Now we can actually further simplify this term over here. So let's see what this term is. So G tau AR, tau dagger, G dagger. Okay. Now this is basically equal to G tau, and then this AR, this is the spectral function of the reservoir. So this is just equal to I GR minus GR dagger. Okay, R for reservoir. Note that this Green's function G is the Green's function of the channel. This Green's function GR is the Green's function of the reservoir. Okay, because this is basically the spectral function of the reservoir or spectral matrix of the reservoir. Okay, so this is I G tau GR tau dagger G dagger minus I G tau GR dagger tau dagger G dagger. Now what is this part? This part is equal to this matrix sigma. This we have learned earlier. So this is equal to I G sigma G dagger minus, and what is this part? This part is basically equal to sigma dagger. Okay, so sigma is equal to tau GR tau dagger, and sigma dagger, this is basically equal to tau. So this would, this complex conjugate transpose of this would come here. We will GR would become GR dagger, and the complex transpose conjugate of this tau would come here. So this becomes tau GR dagger tau dagger. Okay. So minus G sigma dagger G dagger. So this is equal to G, then I sigma minus sigma dagger G dagger, and this becomes equal to G tau G dagger, and tau is basically the imaginary part of this sigma matrix. Okay, so therefore this can be written as integral. So this can be written as integral dE f0 so this is basically should be equal to E, not epsilon, because we are integrating it over energy now. E minus mu G gamma G dagger. Okay, so here also it would be replaced by E because we have the delta function here, so it is correct to replace it by E. So we replace it by E over here. So our entire density matrix now becomes rho equals to integral over dE f0 E minus mu G gamma G dagger. Note that G gamma and G dagger are matrices, but I am avoiding the matrix sign just to avoid clumsiness in the expression. Okay, now this part of this expression over here, this part gives us the energy reserved density of electrons, and we call this Gn, n for electrons over here. And so this matrix Gn is given by F0. So this is a function of energy. Okay, and this is directly related to the density of electrons actually at energy E. So the density of electrons at energy E is directly given by the trace of Gn. Okay, similarly we can have a function for holes which is given by so let me define this function Gp. So P for holes here, and Gpe is basically equal to 1 minus F0 E minus mu, because you can already understand that here it was the occupancy probability. So for holes it should be the probability of vacancy, which is 1 minus F0, then G tau G dagger, and the whole function P of E is basically given by trace of Gp. Okay, now we know that if we compare this expression, with the classical expression, then we have Ne, classically we have Ne equal to density of states dE. So this is equal to density of dE, density of states multiplied by the Fermi function. This is the normal classical picture. Now here we have this Fermi function multiplied by this matrix. So this must, again we can understand that this must be analogous to the density of state. So this must be equal to the spectral function. Okay, so that is the intuitive argument. We can also prove it mathematically. So let us see how this is done. Now we know that the Green's function for the channel is Ei minus H minus sigma inverse. So G inverse must be equal to Ei minus H minus sigma. So G dagger inverse minus G, this is equal to sigma minus sigma dagger, which is equal to minus I gamma. So I multiply both the left side and the right side. I multiply the left side by G dagger and the right side by G. So G dagger inverse minus G inverse, this is G inverse G minus I G dagger gamma G. So this multiplied by this becomes the identity matrix. So the overall it becomes G, and this multiplied by this again becomes the identity matrix. So this becomes G dagger, this becomes equal to I G dagger gamma G. Similarly, we could have multiplied by G dagger here, and we could have multiplied by G here. Then also the equation would come out to be the same. So this is basically equal to minus I G gamma G dagger. So the spectral function of the channel A is basically I G minus G dagger So A is equal to G, so minus goes out because we have multiplied it by I. So G dagger gamma G equals to G gamma G dagger. So we have successfully proved that the spectral function is equal to G dagger gamma G, and this is equal to G gamma G dagger over here. So here we basically get the equation as, let me write it here, this is equal to F0 A, and this is equal to 1 minus F0 times the matrix A. This is a matrix actually. Okay, so from Green's function we have now reached to a way of calculating the electron density and the hole density. Now till now we were discussing a channel with one contact. Now if there are two contacts, so let us assume a channel with two contacts. So this is contact 1 over here, this is the channel, and this is contact 2, and this channel and contact 1 are coupled by the matrix tau 1, and this channel and contact 2 are coupled with the help of this matrix tau 2. So now the Schrodinger's equation for this case basically reduces to the two contact case, which is EI, just like before, it's EI minus H1 plus I eta minus tau 1 dagger, and then it is 0, and here we have minus tau 1, here just we have EI minus H, and then here we have minus tau 2 because the channel is coupled both to the contact 1 via this matrix and contact 2 via this matrix over here. Okay, and then this is 0 because there is no coupling between the contact 1 and contact 2, and this is equal to minus tau 2 dagger, and this is EI minus H2. H2 is the Hamiltonian of this contact 2, H1 is the Hamiltonian of this contact 1, and H is the Hamiltonian of the channel, plus I eta. So I need more space, so let me just make it shorter. This multiplied by phi 1 plus x1. So phi 1 is again the wave function inside the isolated contact 1, and once contact 1 is coupled with the channel wave functions also spill into the contacts or travel into the contacts, and that wave function is basically denoted by this x1. So phi 1 is kind of known because it is a wave function inside the isolated channel, but x1 is not known. Okay, x1 is kind of the influence of the channel on the contact. Okay, and the channel wave function we denote by psi. So let me write it in a smaller font. Phi 1 plus x1. The channel wave function is psi, and then this is phi 2 plus x2, and then this is equal to S1. S1 is the rate at which electrons are replenished into contact 1. So the electron leaks out of contact 1. So this leak needs to be replenished with a source. So this is basically the source term. And we have seen earlier that this S1 and S2 does not come in our calculation because we already assume that EI minus H1 plus I eta, this is a matrix again, so phi 1 is equal to S1. Okay, and similarly for contact 2 we also have the same thing, that EI minus H2 plus I eta phi 2 is equal to S2. So now we also know from our earlier discussion that this x1 is again it's g1 tau 1 dagger psi, and the thing is that everything is the same. Basically the difference is that right now we have two contacts instead of one, where g1 is basically ei minus h1 minus sigma 1 inverse, and g2 is basically ei minus h2 minus sigma 2 inverse, and then sigma 1 is again tau 1 g1 tau 1 dagger, sigma 2 is tau 2 g2 tau 2 dagger, and just like before we have two broadening matrices here which are gamma 1 equals to tau 1 a1 tau 1 dagger, and gamma 2 is equal to tau 2 a2 tau tau 2 dagger. So everything is basically the same. The difference is that just now right now we have two contacts instead of one, and the wave function can still be expressed as psi equals to g times s, where g is the Green's function of the channel, g is ei minus h inverse, and here s we have two contacts, so s is basically s is coming from two terms. One is tau 1 phi 1 and another is tau 2 phi 2. Okay, sorry, we have to write the sigma matrices also in the Green's function. So g is basically equal to ei minus h minus sigma 1 minus sigma 2 inverse. We again ran out of space here, so I'll just put it to the left and write it as inverse. Okay, so now just like before, the spectral function which gives you the density of states is basically given by spectral function of the channel, that is, this is basically given by psi dagger, and this is psi is equal to gs. So gs, and so g and s are matrices. I am not writing the matrix notation here, and psi dagger, so this becomes equal to s dagger g dagger. So then we have this term s dagger. So now what is s dagger? So s dagger is equal to gamma 1 phi 1 plus tau 1 phi 1 plus tau 2 phi 2 multiplied by phi 2 dagger tau 2 dagger phi 1 dagger tau 1 dagger plus phi 2 dagger tau 2 dagger. Now this basically becomes equal to tau 1 phi 1 dagger tau 1 plus tau 2 phi 2 dagger tau 2 plus tau 1 phi 2 dagger tau 2 plus tau 2 phi 1 dagger tau 1 dagger. Okay, so we also have a dagger over here. Actually this cannot be written as a spectral function, it is 2 pi times the spectral function, and it depends on how you interpret psi, so I'm not writing the spectral function here right now. Okay, so note that these two are basically the cross terms, and this term over here, this is basically equal to what is this term phi 1 dagger? This is basically the integral. So let me write in a different page. So phi 1 dagger is basically integral dE AE F0. So we have phi 1 over here, so this is A1 here, then F1. So A1 is the spectral function of reservoir 1, F1 is the Fermi function of reservoir 1. Okay, F1 E minus mu, so I will write it just F1 E, minus mu is implied. So we have a factor of 1 by 2 pi here, so I will write it as multiplied by 1 by 2 pi. So this is equal to 1 by 2 pi integral of dE A1E F1E. Similarly, phi 2 dagger, this is basically integral over dE A2E. We have again a factor of 2 pi over here, 1 by 2 pi integral of dE A2E F2E dE. Now note that F2 is right now we are talking about two contact system, so the channel is coupled to two contacts, and so basically when we are dealing with such situation, we are generally interested in current flow, which basically means there is a voltage difference between contact 1 and contact 2. Now we have learned earlier from our semiconductor device modeling course that when there is a voltage applied between contact 1 and contact 2, then the quasi-Fermi level difference between contact 1 and contact 2 becomes equal to Q times V. Okay, so because their quasi-Fermi levels are different, so these functions F1 and F2E are also different. Okay, and A1E is the spectral function of reservoir 1 or contact 1, and it is related to the density of states in contact 1. A2 is similarly the spectral function of contact 2. This is related to the density of states in contact 2. Okay, so these two terms I can readily write as integral dE divided by 2 pi, then tau 1 A1 tau 1 dagger F1 plus, so these are all functions of energy, but I am not writing that energy argument to avoid making it clumsy. F2, and then these two terms. So this term over here, this term comes from these two terms. Okay, from what I have derived in the later page, that is here. Now these two terms over here, these two terms over here, these two terms are cross terms, and their average is basically 0 because they come from two contacts which are not correlated. Okay, they come from two different contacts. It's not that the wave functions belong to the same contact, so they are kind of uncorrelated, and their cross product, their average is basically 0. Okay, not cross product, but their average is basically 0. So we write it as equal to 0, and so this entire thing, that is psi dagger, so we can write it from here, from what we have derived here. So in this case psi dagger, so the density matrix rho is basically equal to psi dagger, which is equal to integral dE divided by 2 pi G tau 1 A1 tau 1 dagger G dagger, we put a bracket over here, plus G tau 2 A2 tau 2 dagger G dagger, and we have a F1 over here and we have a F2 over here. Now from our earlier discussion, we remember that this is equal to gamma 1 and this part is equal to gamma 2. Okay, so we can rewrite this as dE divided by 2 pi G, and then within brackets we can write it as gamma 1 F1 plus gamma 2 F2 G dagger. This total thing we call it the in-scattering function or in-scattering matrix, and we denote it as sigma in. So this equation totally becomes dE divided by 2 pi G sigma in G dagger. Now what does sigma in denote? So note that this matrix gamma 1, this is basically related to how fast an electron can flow out of the system. Okay, how fast an electron can basically decay once it is put inside the system. So this kind of is related to the velocity of the electron from the channel into the contact. Okay, this is also related to the velocity of the electrons from the channel into contact 2. Okay, now this is related to the velocity of electron, and this is related to the Fermi function of the contact 1. So in total, this total product basically denotes how fast an electron can come from contact 1 into the channel. Okay, this product here denotes how fast an electron can come from contact 2 into the channel. Okay, this term over here also denotes how fast an electron can basically scatter into the channel from contact 1, and that is why this matrix is known as the in-scattering matrix. Okay, it denotes how fast electrons can scatter into the channel from the contacts. Okay, actually we need to put a 1 by 2 pi here, because from what we remember that the density of states is the trace of the spectral function A divided by 2 pi. Okay, so we also need to put a 1 by 2 pi here, which we forgot about last time. The 1 by 2 pi should come here basically. Note that the density matrix can actually be written as integral of dE divided by 2 pi Gn. Okay, so this basically tells us that this Gn is basically G sigma in G dagger, and by the same technique as before, we can basically write this as A1 F1 plus A2 F2. So let us do up to here today. It has already been enough tough, and I believe that you need to think about it and sink this part in a little bit, and the next day we will cover current flow and cover the equation for the current flow through Green's function formulation, and I will give you an assignment where you have to basically model a simulation platform for a resonant tunneling diode. Okay, thank you everyone.